So this is our first numerical problem, and this problem involves steady state heat transfer. We will incorporate most of the stuff that we've learned in chapter 1. So in this particular example, we'll be applying the equations of conduction and convection. So let's dive into it. So for this particular problem, we've taken a solid cube, a cuboid actually. The dimensions of the cuboid are 2 meters, it's 2 meters high, it's 0.5 meters thick, and it's 2 meters deep. The left surface of the cuboid is at a temperature T1, and the right surface of the cuboid is at a temperature T2. And what we've assumed is that the top and the bottom surface of this particular cuboid are insulated. That means they are adiabatic surfaces, so there's no heat transfer taking across those surfaces. Well, when I say it's insulated, it does not mean that all insulated materials are adiabatic or they do not conduct heat. They do conduct heat, but at a slower rate. But for this particular example, we are assuming that the top and the bottom surfaces of this cube are adiabatic. The thermal conductivity of this cube is K, and the value of K is 7 watt per meter Kelvin. We've assumed that there is convection occurring from the T2 surface of the cube, and the surrounding temperature is at T infinity, and the convective heat transfer coefficient is H. The value for H is 10 watt per meter square Kelvin. So for in this scenario, T1 is 450 Kelvin and T2 is 390 Kelvin. So T1, shown in red, is at a higher temperature than T2, which is shown in blue. So obviously the heat will uh, flow from higher temperature to lower temperature. So the direction of heat flux or heat flow is in the positive x direction. Now we've assumed that in the coordinate system, the left surface is at location x1 and the right surface is at location x2, and L is the thickness of the cube. So the given quantities in this problem are H, which is 10 watt per meter square, K 7 watt per meter Kelvin, T1 which is 450 Kelvin, and T2 which is 390 Kelvin. And because the top and the bottom surfaces are adiabatic, the heat flux through them are 0. So moving on to the solution of this problem, the three things that we need to find are Qx. So we are assuming that heat is only flowing in the x direction. So we need to find the rate of heat transfer in x direction, the rate of heat flux in x direction, and T infinity. So let's begin with finding the rate of heat transfer. So to find the rate of heat transfer, that is Qx, we use the Fourier's law, which is minus K into area times dt by dx. This is the Fourier's law. Okay, so let's do so. Many of the people have a question that why do we have a negative sign right here? So let's clarify that first. Now let's take this particular example. Now we know that the we know that T1 is at a higher temperature and T2 is at a lower temperature. So the direction of heat is in the positive x direction. So this quantity right here is a positive. So if your left hand side is positive, the overall right hand side has to be positive. Now let's look at dt by dx. So your dt by dx can be approximated as a final minus initial, that is t2 minus t1 upon x2 minus x1. But t2 is smaller than t1, so this quantity is negative. Okay, so our dt by dx is a negative number, and area is a scalar value. So again, we have a positive number here. Thermal conductivity is a property, so it has to be positive. So if we don't add the negative sign, our right hand side will be negative, but our left hand side is positive. Therefore, there is an additional negative sign which makes the right hand side as positive. So that's why we have a negative sign in the formula of uh, for Fourier's law. Now another thing to note is that if you use this formula and if you assume that the heat is flowing in the x direction and say your T2 was greater than T1, then your right hand side or your heat rate, the heat transfer rate, would be negative, but heat transfer can never be negative. So this just tells you that you've assumed the wrong direction for your heat flow. Okay, I hope this is clear. So let's resume with our problem. So we need to calculate the rate of heat transfer in the x direction. So we can approximate Fourier's law as Qx is equal to minus k times A into delta T. Let's say we are approximating it by delta x, and this can be written as minus k times area into T2 minus T1 upon x2 minus x1. Now our x2 minus x1 is nothing but the thickness of the cuboid, so our formula becomes minus thermal conductivity into area times T2 minus T1 upon L, length or the thickness of the cuboid. So let's substitute the values in here. So our thermal conductivity is 7 watt per meter Kelvin. Our area is 2 meters by 2 meters, so the height of this cube is 2 meters, and depth the depth is 2 meters as well, and the heat is flowing in the x direction, so the area perpendicular to it will be the yz area, or the area which is in the yz plane, so which is 4 meter square. So our area is 4 meter square, and our temperatures are 390 Kelvin minus 450 Kelvin, and our thickness is 0.5 meters. So this gives us a heat transfer rate of 3360 watts or 3360 joules per second. So by approximating the Fourier's law, we got our formula as minus thermal conductivity times the area into T2 minus T1 divided by the thickness. So you can mark this as an important formula, and we got the heat transfer rate in the x direction as 3360 watts. Okay, so the next thing that we have to calculate is the rate of heat flux. So we need to find the rate of heat flux. Now, in our previous video, we saw that heat flux denoted by Q double prime X is nothing but the heat transfer rate. Sorry, is the heat transfer rate divided by the area, and the area is perpendicular to the flow of heat. So in this case, our heat transfer rate that we got was 3360 watt, and our area A is 4 meter square. That's the area, that's this thickness right here, which is 2 meters, divided by this particular edge right here, which is 2 meters. So it's the area of this particular surface. So plugging in these values, what we get is that we get 3360 divided by 4, which gives us 840 watt per meter square. So our rate of heat flux in the x direction is 840 watt per meter square. Now the third thing that we have to find is T infinity. Now what's happening in this problem is that there's heat being transferred from this surface, from the surface T2 to the surrounding because of the temperature difference between the surrounding and the surface. So the surface is at a temperature T2, surrounding is at T infinity, and the mode of heat transfer will be convection. So we will have to find T infinity. We would have to know what is Q convection. Now the important thing to note here is the problem that we are solving is a steady state problem. It's actually conduction and convection. And what steady state means, so let's note that we have assumed steady state, and what that implies is that temperature is not changing with time. Okay, so your T1 will remain constant with time, T2 will remain constant with time, and T infinity will remain constant at with time. So what this means? This means is that for T2 to remain constant, the heat transferred by conduction must be equal to by conduction must be equal to heat transfer due to convection. Now, how can we prove this? To prove this, we'll have to look at the energy balance equation. So let's look at the energy balance equation at this particular surface, which is T2. Okay, so let's consider the interface. Let's consider interface T2, and let's look at the 2D cross-sectional view of T2. So when we take the side view of T2, we will just be looking at a single edge, and the temperature of this particular surface is T2. The temperature of the surrounding is T infinity. We know that the left side of this particular surface is the cuboid, and there's a heat transfer due to conduction in this direction, which is the qx that we computed uh, just right now, and there will be a q convection, heat transfer due to convection happening uh, because of the temperature difference between T2 and T infinity. Now for T2 to remain constant, Q conduction must be equal to Q convection. If either of the two are smaller or bigger, your T2 will change with time, because you will either be storing energy into the system or removing energy into the system. So to understand this further, let's look at the energy balance. So this is location x2. So let's look at energy balance equation at x2, and the energy balance equation will be EST, energy stored per unit time, equals Q in minus Q out plus Q generated. Now excuse me, now there's no heat being generated in the system, so this term goes to 0. Now our left hand side, that's the EST, the energy stored per unit time, can be written as m Cp into del T by del X. I'm sorry, this will be del T by del time, which will be equal to Q in to this system, which is Q conduction, minus Q out, which is Q convection. But because we are looking at a steady state, because we assumed that our problem is at steady state, therefore your del T by del T, your partial derivative of temperature with respect to time, will be 0. Your temperature will not change with time. So your left hand side is 0 and your right hand side is Q conduction minus Q convection, which means that your Q conduction equals Q convection, and your Q conduction is nothing but your Qx. So your Qx will be equal to Q convection. So let's apply the Newton's law of cooling. So your Q convection will be the heat transfer coefficient into the area into the temperature difference delta T. So this can be written as H A times T2 minus T infinity. So let's plug in the numbers. So our H is 10 watt per meter square Kelvin. Our area is 4 meter square, and our temperature T2 is 390 Kelvin, minus T infinity is unknown that we need to find. So our meter square cancels out, and Kelvin will cancel out eventually. And so our temperature T infinity will be 306 Kelvin, which is approximately 33 degrees Celsius. So this is how you apply your Fourier's law, your Newton's law of cooling, and your energy balance equation to calculate either the heat flow rates, the heat transfer rates, or the heat flux, or the temperatures which are unknown.